Great. Welcome in everyone for another N3AS seminar. Today we're excited to have Gang Guo from China University of Geosciences in Wuhan to tell us about collapsars as sources for high energy neutrinos and R-process nuclei. Please, whenever you're ready, Gang, take it away.
Okay, thanks. So my today's talk will be focused on my recent work with Yongzhong Chen and Mengru Ru. So actually now we have a revised version for this paper. We plan to post it on CAV recently. Okay, so today I will talk something about the collapsar. So collapsar produced by the collapse of massive star into a black hole surrounded by accretion disk, and is responsible for power the non-GRB non-gamma ray burst. So relativistic jets could be launched from the accretion disk, and they are responsible for the burst of gamma rays, and also they can produce high energy neutrinos. Along with the relativistic jets, so some non-relativistic outflow can also be ejected, and they are responsible for the making up-produced nuclei. So it's actually become possible to have a multi-messenger observation of the collapsar via the electromagnetic signals in different bands, neutrino with low and high energies, and also gravitational waves. Today I will focus on the neutrino side. Okay, my talk will be divided into two parts. So in the first part, I will revisit high energy neutrino production models inside the progenitors of collapsar. And in the second part, I will introduce a so-called a local collection between the high and the low energy neutrinos from collapsars. So the basic picture is that the high energy neutrinos produced by shocks could be annihilated by the low energy antineutrinos from the beta decay of the newly synthesized nuclei. And such annihilation could have some impact on the spectrum and the flavor composition of the high energy neutrinos. Okay, so that's the very basic picture of this work. Okay, in this slide, I want to go very briefly the high energy neutrino. Okay, so in this slide, I want to briefly go through the high energy neutrino productions in gamma ray burst or called supernova. So actually, the charged particles can be accelerated to high energy by constantly crossing the shock front. And another important factor is that when they during the acceleration cycle, the charged particles have some certain probability to escape either into the downstream or the upstream. And from the simulations, the spectrum of the proton can be described by a power law with a spectral index between 2 to 2.2. And actually, the shock acceleration is quite complicated, depending sensitive on the Lorentz factor of the fluid, the strength and the configuration of the magnetic field in the fluid. And in this equation, I also introduced the EP max. This is the maximum energy accelerated in the shocks. And it basically can be determined by the balance between the acceleration timescale and the cooling timescale. So when we have high energy protons, they can interact with the either stellar matter or the photons inside the environment via the so-called PP or P gamma process. We have some unstable charged mesons, then they can decay to high energy neutrinos. And I want to emphasize that the cooling of the charged mesons in the jets to suppress the produced high energy neutrino flux. Because when the magnetic field is strong enough, the charged meson would cool down very fast before decay. So the neutrino flux will be suppressed at high energy end. And there are actually many various sites for high energy neutrinos in the gamma ray burst, depending on how and where the shocks are produced. Here I need some basic possibilities. When the jet penetrates through the stellar envelope, they can produce internal shocks or the external shock, which are responsible for the prompt radiation and the afterglow of the GRBs. And in those two kinds of shocks, the so-called prompt neutrinos and the neutrino afterglows can be produced. And when the jet is still propagating inside of the stars, different kinds of shocks can also be formed, like the internal shock before the jet collapsation. And also we have some collapsation shocks. So when the jet glides into the stellar matter, it can produce an external or reverse shock driven by the jet head. And along with all those different kinds of shocks, high energy neutrino can be produced. In this talk, I will focus on high energy neutrinos produced deep inside progenitor star. So firstly, I'd like to mention a few drawbacks of high energy neutrino produced close to the central energy. The first drawback is that when the radius is very small, the magnetic field in the jet will be very high. Now, basically, the B square can be determined by epsilon B times L divided by gamma square R square. Here, epsilon B is the energy fraction going to a magnetic field, and L is the jet luminosity. Gamma is the Lorentz factor, and R is the shock radius. So we say that if R is very small, then the magnetic field will be very large. If the magnetic field is large, then the synchronous cooling of the charged mesons will be very fast, and the high energy neutrino flux will be suppressed. So that's the first drawback if the production site is very close to the center. The second drawback is that if the radius is very small, then the radiation energy density is very high. Now we have a very similar formula. Here, epsilon E is the energy deposited, dissipated in thermal energy. If the radiation density is very high, here I show this is upstream, this is downstream. If the radiation is very high, then the coupling between the radiation and the charged particles will prevent the charged particles causing from the shock front. And in this case, the acceleration will be very inefficient. And from the study by Mirazi and his collaborators, so to form a collisionist internal shock, we should have a very low velocity for the jets, and the radius should be larger, and the jet should be fast. So by fast, I mean the Lorentz factor of the jet should be large. And such kind of possibility has been investigated by Mirazi. Now, if the luminosity of the jet is high, then the high energy neutrino production will be prohibited. Okay, so is there any possibility to avoid such kind of constraint? There's actually some possible way out. Let's say if the jets are sufficiently magnetized, then we are still able to form a collisionist internal shock following the radiation-mediated shocks in the downstream side. So the pictures look like this. So here we have the radiation-mediated shocks. Basically, the shock has been smoothed by the high radiation density. But still, we have subshocks with a very thin shock front. So the width of the subshock is close to the proton llama radius. But for the radiation-mediated shocks, the width is basically determined by the photon beam free path, which is very large than the proton llama radius. So if you have a very wide shock front, then the energy cooling is very sufficient. So the acceleration at the radiation-mediated shock is very inefficient. But when the particles causing the subshock, because the subshock has a very thin width, we still have a very sharp density jump in the subshock regions. So particle acceleration is still efficient. Now from the studies by Bilo-Baradov, so to form a conditionist subshock, which supports particle acceleration, the radiation density should be close to the magnetic energy density. Now here I introduce two parameters, WD and sigma D. Sigma is the ratio of the thermal ratio energy density to the rest mass energy density, and sigma is the ratio of the magnetic energy density to the rest mass energy density. So basically, D here denotes the downstream, and U stands for upstream. So if WD is close to sigma D, which means if the magnetic field energy is close to the radiation energy density, then we're still able to have a subshock, conditioning subshock. We can further use this jump condition, and this equation, WD close to sigma D, can be transferred to this equation. So basically, we need sigma U. Sigma U here means this upstream. So the magnetization of the pre-shocked jet should be larger than 0.01 to 0.1. So basically, we can say that in this picture. So the contours show that. So they are the contours of WD equal to 2 sigma D. And here is sigma star. So sigma U should larger than sigma star. Okay. And besides, the amide magnetized also has to avoid strong mixing of the jet with the sterner matter and can achieve a fast jet. I want to emphasize is that a fast jet is quite essential to produce high energy neutrinos, because when the Lorentz factor of the jet is larger, then the magnetic field is lower. If you have a lower magnetic field, then the high energy neutrino flux at the high energy end could be higher. So because you can avoid the strong synchrotron cooling of the charged mesons. But there's also some drawback. So if the jet itself carries some magnetic field, then such magnetic field can also be further enhanced by the shock compression. And you expect to have a very larger magnetic field, and such a larger magnetic field will further suppress the high energy neutrino flux in the shocked plasma. So we want to introduce magnetic field to avoid the radiation constraint. But when you include a magnetized jet, the magnetic field could be even larger, which can on the other hand suppress the high energy neutrino production. So actually, in our study, we tend to consider high energy neutrino production in the unshocked jet, which means the upstream of the shock. So here, the unshocked jet means the upstream of the shock, and the shocked jet means the downstream of the shock. So in the upstream, we have the possibility to have comparable flux of accelerated proton in the upstream regime. So from the recent kinetic simulation of the mildly reduced shock by Krumlai, so we can see that at the high energy end, the accelerated proton flux is even higher than that in the downstream. And secondly, close to the center, we still have high number density for the targeted proton. And also, when you close to the center, the jet is still hot enough to have many thermal photons. So we have enough proton targets, we have enough photon target in upstream. So the possibility, we have the possibility to produce high energy neutrinos in the upstream of the shock. And this possibility has been barely discussed in the literature. Okay, so basically I have set up everything needed to talk my high energy neutrino production models. So we consider high energy neutrino production at internal shock, the inside progenitor star. And the internal shock actually caused by a faster, luminous, mildly magnetized jet before acclimation. So in our benchmark study, we take some typical values for those parameters. So R is the internal shock radius, and the ISO is the isotropic luminosity of the jet, and gamma is the Lorentz factor of the jets. So sigma U is the magnetization in the upstream, and sigma D is the magnetization in the downstream. They are collected by the compression factors. So the compression factor is about 5. So basically, it relates some quantity in the upstream and the quantity in the downstream. Okay, so if we have all those values, we can calculate the magnetic field, the proton targets, and the photon temperature in downstream and upstream. We have all these values, we can calculate high energy neutrino flux. So we assume the accelerated proton follows a power law distribution. And we use Python PCL8 to calculate the PP yields and Sophia to calculate the P gamma yields. And for the pion cooling, we calculate the cooling scale and the decay scale, and we compare them to calculate the neutrino flux. Okay, in this slide, I show the relevant time scales for proton and the charged mesons. So in the left figure is for the time scale of proton, the acceleration time scale, and the cooling time scale. So for the cooling process, I basically consider all the process, like the P gamma process, the Best-Heitner process. Like for Best-Heitner process is basically the proton plus a photon to an electron-proton pair, and also the adiabatic cooling of protons in the shock in the jets. And similarly for charged mesons, for charged meson, we consider the decay time scale and also the other cooling time scales. So the x-axis shows the proton energy, the meson energy in the moving frame of the jet. And if we want to have the energy of neutrino in the lab frame, then we need to consider the boost factor and also the energy fraction going to neutrinos. So the neutrino observed energy is given by roughly by 2.05 times the Lorentz factor of the jet and the proton energy, and 0.25 gamma sigma r e pi, and 0.5 gamma r ek. So using this equation, they will basically can find the corresponding energy of protons or mesons. So the corresponding energy to 0.1 PeV neutrino and the PeV neutrino. We see in the depth in this figure that in this typical region, the acceleration is the fast. So let's just say the proton can be accelerated to high electron energy to make PeV neutrinos, because in this energy range, acceleration is the fast time scale, is faster process. Okay, so in this process, we can say that. Okay, so the red line shows the decay time scale of pion, and the others are for the cooling time scales. So between this region, we see that the pair production and the synchrotron cooling are the dominant process for pions. Now here, the pair production means the pi plus pi minus plus a photon to produce electron-proton pair. Okay, so if we see this figure, we find that the time scale, the decay is very slow compared to the cooling process. So this is what I meant, that the cooling can strongly suppress the high energy neutrino production. As a comparison, we basically have a better situation for pions, because of the ratio of the kaon, the decay time scale is not too small than the cooling time scales. So for high energy neutrino production, kaon contributes more significant than pion decay. Okay, so before showing the results of the high energy neutrino flux, I want to talk a bit about the low energy neutrinos from the beta decay of the synthesized elements. Now, recently, Sago and his collaborators has shown that the outflow in the accretion disks from collapsar are very close to in the bioevolution stages, and they propose that collapsar could be a dominant source for R-pros nuclei. Now, if this is the case, then we basically have a profuse low energy neutrinos emitted from the beta decay. And they can annihilate with the high energy neutrinos. And such annihilation can change the spectrum and the flavor composition of the high energy neutrinos produced by the shocks. Okay, so beta decay dominates the nuclear heating rate. And the heating power is a constant within the first second, and follows a power law decay. So basically, from the heating power, we can estimate the low energy neutrino flux. So the power of the beta decay is roughly 10 to 19 ergs per gram per mass per unit of time. And eta t shows the temporal evolution of the heating power. And here we have a parameter tr. So basically tr is about 1 second, showing the length of the plateau. So the power divided by the average energy of low energy neutrinos gives us the emission rate. And the term in the brackets shows the normalized spectrum of antineutrinos. Basically, they are purely from the phase space. So in this approximated form, we neglected all the nuclear effects. And the average of the low energy neutrino is roughly is around 4 to 5 MeV. So if we load the emission rate and we can do the integral, we can get the neutrino flux or intensity at a given radius, a given angle, and for a given energy of the low energy neutrinos. So basically, it's given by the integral of the two terms and the length, the integral of the length. And in this equation, rho r is the ejector mass density. If we assume the outflow is spherical symmetric, then the rho is simply given by m dot divided by 4 pi r square Vej. So m dot is the ejector mass loss rate. So it's around 0.01 to 0.1 solar mass per second. And V ejector is the velocity of the ejector, around 0.05 times speed of light or 0.1 speed of light. Okay, so if we have all the values, we can calculate the density or the flux of low energy neutrinos. So this is all we need to calculate the annihilation between the low and high energy neutrinos. So prior to the annihilation point, we also need to consider the oscillation of the low energy neutrinos. So initially, only electron antineutrino are produced from beta decay. And after oscillation, we have also other flavors. So inside the star, if the density varies very slowly, so basically means that the neutrino flavor can evolve adiabatically, then we only need to consider the density at the emission point and the annihilation point, which are denoted by A and B. So for the annihilation point, because annihilation occurs inside the jets, where the density is typically below 1 gram per cubic centimeters. So rho B is very low. But for rho A, we don't know the exact value because rho A can span a wide range. If the density here is dominated by the wind or by the ejector, then it's of order 10 to 3 gram per cubic centimeter at the radius close to 10 to 9 gram per centimeter. If the density here is dominated by the stellar mat, then the density could be higher, reaching 10 to 6 gram per cubic centimeters. Okay, so we have a very low density for point B, and for point A, rho A is quite uncertain, spanning a wide range. So to consider neutrino oscillations of the low energy, we consider two extreme cases. So first, we consider rho A is very low. And if density at A is low, the density at B is low, then we basically have expected a vacuum oscillation. Okay, so we also consider a lot of cases that rho A is very high. So if rho A is very large, then 10 to 4 gram per cubic centimeters, then the initially produced electron antineutrino will be identical to nu1m for the normal neutrino mass hierarchy and nu3m for the inverted neutrino mass hierarchy. And here nu1m, nu3m is the mass eigenstate immediate. Okay, so at point B, we only need to project those mass eigenstates into the flavor eigenstates, and then we can have the oscillation probabilities. So for the pure vacuum oscillations, we have the rate. We have such a flavor composition: 0.555 for electron neutrino, 0.18 for muon, 0.27 for tau. And also for we have similar results for the other two cases. And I will show later that our high energy neutrino flux is dominated by a muon flux. It's dominated by muon flux. So for the low energy neutrinos, only p nu mu, the middle value is relevant. Because to annihilate high energy mu neutrinos, only the muon antineutrino are relevant. So these three values is quite important. And we basically say that for those different oscillation scenarios, the p nu mu could be vary by a factor of 5. So this is the smallest value, and this is the highest value. And if p mu nu is very large, then we basically expect a more significant annihilation effect. And in our benchmark studies, we consider the vacuum case. Okay, so basically we have everything we had, and then we discuss how we calculate the neutrino pair annihilation. So the first point I want to mention is that suppose the relativistic jets and the non-relativistic wind or the ejector launched almost simultaneously after the formation of a accretion disk. So they could have some time difference of order a few seconds. But because the duration of the accretion process is quite long, it could be a few 10 seconds to 100 seconds. So this tiny difference is irrelevant. And in this sense, we say that the high energy neutrinos can meet the low energy neutrinos. Okay. So secondly, we simply assume that a steady low energy antineutrino background. So they are steady, static, because we basically assume a constant mass loss rate. And to study the neutrino pair annihilation, we construct a 1D Monte Carlo simulation code to simulate the neutrino pair annihilation. We also take into account the secondary process. Because in the pair annihilation, it can produce a pair of quarks, a pair of charged leptons, and a pair of neutrinos. So the produced pion, cation can also decay to produce neutrinos. And similar for the charged leptons like muon and tau. So in our simulations, we also include those secondary process. And we use PSA8 to calculate the neutrino pair annihilation yields. And for the decay of the mesons, we only include the dominated decay channels. Okay, so in this slide, I show the results for the high energy neutrino flux. So in the left figure, we show the neutrinos, the flux for neutrinos and antineutrinos. And in the middle panel, we show neutrino flux for different flavors. We show nu e plus nu e bar, nu mu plus nu mu bar, nu tau plus nu tau bar. And in the right panel, we show the total flux using different jet luminosities. And the solid line shows the neutrino flux considering the neutrino pair annihilation, and the dashed lines without considering the neutrino annihilation. So we see in the left figure that we basically have comparable flux for neutrinos and antineutrinos. So the reason is that in the low energy regime, the PP process dominates. And because the center of mass energy is very high for PP process, so basically the equal amounts of particles and antiparticles are produced. And at a high energy regime, the P gamma process start to dominate. And in P gamma reaction, pi plus are more abundant. So we expect a higher flux for the neutrinos. So if we look at the middle panel, we can see that the flux is basically dominated by mu neutrinos. This is naturally expected because the muon is strongly suppressed. So we only have mu neutrinos from the pion decay or the kaon decay. And the decay of muons are highly suppressed. So we have a neutrino dominated flux and also mu neo dominated flux for the high energy neutrinos. And if in the so we look at the right panel, we see that so the inserted figure shows the ratio between the flux, considering without neutrino annihilation to that including neutrino annihilation. So basically, if we consider the neutrino annihilation, we would have a suppression of the flux by a factor of 3, above a few hundred TeV for the high energy neutrinos. Okay, so that's the basic results for our study. And if we want to compare our results with the ice cube data, so we need to calculate the diffuse high energy neutrino flux. And instead of integrating over all the contributions, we use a very simple formula to estimate the high energy neutrino flux. So here, C divided by 4 pi H0, so H0 is the Hubble constant, so basically gives the effective distance of the source. And N dot GRB is the rate of gamma ray burst. And the other parameters, FCR, E iso, and the log EP max divided by EP minimum basically is the normalization factor for protons. And note that we introduce another parameter, F star. So F star is the ratio of collapsar rate with mildly magnetized jet to that of bright GRBs. Because for collapsars, we expect to have a much higher rate for the low gamma ray, low luminosity GRBs, or even the choked GRBs. So also the high energy neutrino flux are actually dominated by these because they have a higher occurrence rates. In our study, we also assume that all those jets, they have similar properties. They have a similar luminosity, opening angle, and noise factors. So even for the low luminosity GRBs. So if we input the F star, then we can get the diffuse flux. So another issue I want to mention is that, so the stacked processor search at ice cube has constrained the contribution from bright GRBs to be within 10%. So with the parameters chosen in our study, such a constraint has not been is not violated. So it's still allowed by the current data. In our benchmark study, we assume vacuum oscillation of low energy neutrinos and the spherical wind for the outflows, the spherical geometry for the outflow. And we can also consider the MSW plus normal hierarchy case. So basically, the flux will be reduced by a factor of 2. The flux for low energy neutrinos will be fluxed by a factor of 2. So the winds could be also climate. So it's not spherical symmetric. It could be also asymmetric. So it could be confined into a certain angle, like confined to 0 degree to 45 degree. In this case, the flux of the low energy neutrinos will be enhanced by a factor of 3. And in this case, we have very similar flux for the low energy neutrinos compared to our benchmark case. So we consider all those different assumptions, and we find that the annihilation is significant for all all cases. Now this plot shows a comparison between our results to the ice cube data. So for the ice cube data, we only show the cascade results denoted by the cost point. And we say that so in this energy regime, basically above a few hundred TeV, there seems to be a drop in the ice cube data. And we say that this can be well explained by our studies. And also here we have a bump. So the bump is basically due to the increasing of the kaon contribution. Okay, in this slide, I want to discuss the prediction of our high energy neutrino models. So to test our model, we expect to say the precursor neutrino blast from a nearby low luminosity GRBs. So if we take some benchmark values for the jets, we can say about 10 cascades at ice cube Gen 2 from a nearby low luminosity GRB at a distance of 100 megapc. And the duration of the neutrino burst is around a few 10 seconds. So if we do say such a kind of signals, then we can test the models of low luminosity GRBs. So for the flavor composition, our flux show that it's dominated by the mu neutrino. Because when you produce the highest neutrino inside the star, we have a strong cooling to suppress the neutrino flux for the other flavors. And such kind of flavor composition can be clearly observed at ice cube Gen 2. And it can be distinguishable from the standard pion decay scenario with a composition about 1 to 2 to 1 at source. So those two different compositions can be clearly distinguished. So if collapsar are a source for R-process nuclei, then we may expect some pair annihilation effects. And such annihilation could cause a sudden drop in the diffuse spectrum. Okay, so in this slide, I also discussed, we studied the possibility of observing such a drop in the diffuse neutrino flux at ice cube Gen 2. So to observe, to obtain the sensitivity, we carry out a sensitivity study using ice cube Gen 2. So basically the flux can be described by a broken power law from our studies. So above some break energy, EB, so EB is around 100 to 200 TeV. Then the spectrum has a spectral change about 2.5. So we assume such kind of simple form for the neutrino flux, and then we generated so-called Asimov data, assuming some typical values. So basically, the Asimov data set means that we ignore the statistical fluctuation when we generated neutrino the data. So we use 10 years of ice cube Gen 2 data, and we consider only the atmospheric neutrino as the background. We define the chi-square like this, and we've tuned to the two parameters. We tuned the delta gamma and 2 EB to get contours of delta chi-square equal to 5.99. So this figure shows the contour in the delta gamma and the EB plane. We say that using the 10 years of ice cube Gen 2 data, a spectral change greater than 1 can be observed at the confidence level of 95%. So this is very good. Now I think I need to summarize my talk. It's a bit fast. So firstly, I want to emphasize a few new features I have considered in the neutrino production model. So we consider the conditionist subshock induced by the mildly magnetized jets. And we consider high energy neutrino in the upstream of the shock instead of downstream. So this is a very new. And we also find that the pair annihilation is relevant for cooling of charging mesons. And this has not been discussed in the previous literature. So if collapsar are a possible source for R-process nuclei, then we may expect the annihilation between low energy neutrinos and the high energy neutrinos. And such annihilation can leave some influence on the spectrum, the flavor composition of the high energy neutrino flux. And all those signatures can be tested and observed by the future neutrino telescope. And the last point I want to emphasize is that similar studies can also be applied for bilevel neutron star mergers or short GRBs. Okay, so thanks for your attention.
Thank you, Gong. Do we have any questions? Please raise your hand. So while folks are thinking, so I had a question going on slide 10.
Slide 10.
Yeah. Yeah, I was just curious. So you have this fit formula, right? And there's that plateau and then the decay.
Yes.
And it looks like at very early times, there's some, there's the different nuclear reaction networks disagree a bit, and then they disagree from the plateau in your fit. Does that matter at all, or is that just because it's such early times, it's not really sensitive to that?
No, I think it depends on the YE you assume. So, and also
Yeah.
this is a very old results. So from the recent simulations, you say that this formula is quite good to describe the power. So a constant power followed by a decay.
Mm-hmm. Okay, so there shouldn't be too much sensitivity then in your annihilation.
So I think there are 4
results
different YEs. There are 4 different YEs.
Mm-hmm.
So if the YE, so we choose YE equal to 0.2, and then quite good. It has a quite good shape.
Mm-hmm. Okay, thanks. It looks like we have a hand from Zidu. Please unmute yourself and ask your question.
Oh, yeah. Okay, so can you hear me?
Yeah, it's not so clear. It's not clear.
Okay, I will try to somehow increase my voice. Yeah, thank you for the interesting talk. Yeah, but yeah, I'm interested in a lot of things that you talked about, but at the same time, I don't quite understand a lot of things from this talk. So
Okay.
yeah, what is the relationship between the high and the low energies neutrinos here?
You mean the relation?
Yeah, what is the relationship between the low and the high energy neutrinos? I'm sorry, I missed that point.
Okay. So then you have only one question or you have another? Okay.
It's just
So
one question. Yeah.
Okay, so they are produced as they have different production mechanism. So the high energy neutrino actually produce at shocks. So it's caused by the relativistic jets.
Yeah.
The low energy neutrino are from the beta decay from the non-relativistic outflow.
So they are produced at different locations.
Yeah, they are produced at different locations, different mechanism.
Right. Then what is the relationship between these two? Or because I think that if I understand correctly, you told us that they are somehow relating to each other.
So in our study, they are kind of separated. They're kind of independent. You know, you can say that in our formula for the low energy neutrinos is simply determined by the the mass loss rate and the ejector velocity and also the heating power,
yeah.
the power.
Yes.
And for the high energy neutrinos, it depends on the property of the relativistic jets. And I think there should be some correlation between the relativistic jets and the non-relativistic outflows. There could be some relations.
Yeah, probably I somehow misunderstand some points from your talk. But then why do we need to know the properties about the low energy neutrinos to do this study?
You mean the neutrino oscillation of low energy neutrinos?
Yes.
Okay. So the low energy neutrino initially produced puny electron antineutrinos from beta decay.
Right. Yes.
And here for the high energy neutrinos, we have a flavor composition. We have mu neutrino, electron neutrino, and the others. And I mentioned that the high energy neutrino flux is dominated by mu neo. It's dominated by mu1 neutrino. And if we consider the parallelization between the low and high energy neutrinos, we know that the annihilation between same flavors is dominant because we have a Z resonance So the cross section is enhanced. So to annihilate muon high energy neutrinos, we need to have a low energy muon neutrinos.
I see. Okay.
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 So that's why we need to consider the oscillation of low energy neutrinos.
I see. Okay, that makes sense. Okay. Yeah, I have another question. So for the production of those high energy neutrinos, what is the local density over there when those high energy neutrinos are produced? The local, for example, the local number density of those protons.
The number density is not high. Here I show the typical values. So because high energy neutrino actually produce inside the jets, so inside jets is simply determined by the jet, and
Okay.
and the density is basically below 1 gram per cubic centimeters. And for the proton number density should be of the order of Avogadro constant 10 to 23.
I see. Okay, I see. Yeah, the last question. So do you think that this kind of the high energy neutrinos are somehow correlating with the gamma ray burst? I mean, how can we somehow, understand or study the gamma ray burst by investigating the, for example, the energy spectrum of those high energy neutrinos?
So
I don't know too
actually
much
for bright GRBs, let me go to this slide. Okay, so for bright GRBs, so you know the reason for the burst of gamma ray burst. So because the electrons can be accelerated to high energies
Yes.
at the shocks, and those accelerated electrons can emit gamma rays via single-channel radiation. So that's the arranging of the gamma ray burst. And at the same site, the accelerated proton can produce high energy neutrinos.
Yes.
So we can have a correlation of the high energy neutrino and the gamma rays. So that's how IceCube search for neutrinos from gamma ray burst. So basically, they search, they do a correlation search of the gamma rays and the high energy neutrinos. But in this talk, I talk about the high energy neutrino produced inside the jets. So basically, we expect low gamma ray signals.
I see. Okay.
And from those precursor high energy neutrinos, we're able to probe the inner structure inside the projected star.
I see. Okay. Okay, great. Okay, thank you so much. Yeah, that's interesting.
Okay.
Do we have any more questions? I don't see any more hands, so let's thank our speaker again.
Thank you for your attention.
Great, and we hope to see everyone again in 2 weeks.